Okay, let's do a couple from the written homework. Let's do the napkin holder. You want to do the napkin holder? Maybe. Let's see if I can try this. Just set a timer. Again. You just set it down on the top. I'll get it in there. That's fine. Something like this. And so this is a hollowed out sphere, and we're trying to find the volume of what remains after we hollow it out. So our inner radius is little r, and our outer radius is big R. Didn't leave enough room for that. Do it down here. The outer radius is big R. And the height of the whole thing is h, is that right? Is that right? The whole thing is h?
Yeah.
Okay, so we need to base this on, of course, we're going to base this on a sphere. So we need the equation of the circle, and we're thinking about rotating that circle, say, around the y-axis. So if we think about what is the sphere that it comes from? Or what's this circle? So I think we want to maybe put to make it easier on ourselves, we want to put that thing right on the center. Put the center of the sphere, or the center of the circle on the origin. And then we need this circle, and we think about, we're just going to rotate this circle, say, around the y-axis. And we're going to look at a typical slice like this as it rotates. And it's going to make a shell, right? If we rotate that. And that's going to make a circular shell. And so we're going to get the volume of that shell right there. Okay, so what are the coordinates of this point right here? So if we're using our x and y axis like this, then that's going to be an important point right there. What's the coordinates of that point? X coordinate is? Yeah, so this is x, right? So this has x coordinate of x to here, but this particular point where we've shaved off the top. Can you take off all the side for me? Can you give me a clean left edge? So what would that be?
Capital R minus small r.
This x coordinate at this point? Just little r, right? And then what's this y coordinate? Is it h over 2? H over 2. Okay, and what's the equation of this circle that we're going to rotate around the y-axis? The x squared plus y squared equals? Which r? Big R squared. Okay, so we're going to take that circle and we're going to rotate it around the y-axis, and that'll give us the solid that we want, and then we're going to take the volume of it. We're going to add up all these blue shells. We're going to add up the volumes of all these blue shells. So the volume of the shell will be the circumference of the shell times the height of the shell. So I'll call that, so the height of the shell we need to call something else. So let's call that capital H. Because the height of the napkin holder and the height of the shell is two different things. And then we're going to have, is it going to be times the thickness? Is the thickness delta x or delta y?
Delta x.
Delta x. Okay, so we need to find the radius. If we can get the radius of our shell and the height of our shell in terms of little r and little h, then we'll have it. So what's the radius of our shell? The radius of our shell would be from here out to our shell. Which would be, now we're talking about this point. So what's the radius of our shell in terms of x, y, little r, little h? So what is the radius of our shell? So it's from here to here. If you're looking at that point right there. From there to there. Just x, right? It's just the x coordinate of that point to get the radius of our shell. Were you thinking that? Hopefully we're starting to see this now. Okay, so this point determines the radius and height of our shell, this point right here. And so its x coordinate is the radius of the shell. And so it's just x. Okay, what's capital H then? What's capital H? Well, capital H then is going to come from the y coordinate of this point. It's actually going to be 2 times the y coordinate of this point. So 2y. So now we just got to find out what, since we're doing delta x, we got to get y in terms of x. What is y in terms of x? Y is? So here's where we're going to get y from, right? Because it's on this circle. It's on this circle, so we're going to square. We're going to solve for y in that equation. So capital R squared minus x squared. And I think we got it. That's the volume of a typical shell right there. Okay, questions on that? All right, so then we're going to sum up all the shells. So that. Okay, there we go. So we're going to sum up all the volume of all the shells. So the volume of the napkin ring equals, we're going to have 2 pi x times 2 squared minus x squared dx. Okay, and we're going to go, x goes from what to what? So the least value of x, or the first inner shell, is going to be right here at the edge of the hole, right? So what x value is that there at the edge of the hole? R, right? And then the last shell is going to be way out here. It's going to be a really short, it's going to be the widest shell. It's going to come out to here. What value of x is that? Bigger. Okay? Any questions? Does it make sense? And notice what happened. When we look at this integral here, what do you notice? So we can say 4 pi Okay, so first of all, to evaluate that, we all should recognize that as undoing chain, because why? Because derivative of this x squared, here it is, x, or a factor of it, right? A multiple of that. So we can undo chain or use substitution, whatever you want. Okay, so that's nice. But then what do you notice about this whole thing? What is not there? Yeah, there's this little h here is nowhere to be found. So we got the volume of this thing, and I think they asked you to compare like the volume of a different, if you started with a different size sphere but made the height the same, how would the volumes compare? Right? So how would they compare? So because if the height's the same, even if you choose a different, well, let's see. But it's going to depend on capital R, right?
I think it comes down to depend on if the height's the same, then it's the same amount of work regardless of the size of the
All right, let's see what happens here. So we get r squared minus x squared to the 3/2, and we need a 2/3, and then we got what? -2. If we took the derivative, we'd have -2x, which we don't have. We don't have a -2x, so to compensate, we need -1/2. We'll go from little r to big R. Okay, so when you plug the big R in, what happens? First term, 0, right? This makes 0 when you put big R in. So all we're going to have then is the second term, which is, this will be minus a -1/2, so that makes plus. So it could be 1/2 times 4 pi times 2/3 times what? Big R squared minus little r squared. So we got 4 pi over 3. Is this familiar for those of you who got it? Is that familiar? Does that seem right? Did I do all the math right? Question?
I thought my answer was like had terms of h.
It had h in it.
We had to do it in terms of h.
Had to do it in terms of h.
You can just replace the big R.
Yeah, but big R and h are two different things, right? So where did I go astray here?
Well, if you replace big R with x squared and y squared, you realize that y is h over 2.
Oh, okay. So at this point right here,
Right.
using this equation?
Yeah.
Okay. I see. So for this point, this is where h comes into it right there. So that would say that r squared plus h over 2 squared equals big R squared. Okay, and so then we can plug in for big R squared, we plug in this expression, and then we'll have r squared minus r squared. So we'll just have the h over 2. So I need more room here. So I have 4 pi over 3 times, and so capital R squared is little r squared plus h over 2 squared, and then we'll have minus r squared, so the r squares will go away. So all we'll have is h over 2 squared to the 3/2. So that's good. So the point is now that it doesn't depend on big R, right? It doesn't depend on the size of the sphere if you keep if your H is the same, your napkin holder volume is the same. So what is that? H. I'll just leave it. That's fine. That can be simplified a little bit more, but that's not the point of the problem. Okay. Any questions on that one? Okay, what about deriving the equation of a cone, volume for a cone? So my hint to you was put the vertex of the cone at the origin, right there. And so if you imagine something like this. So, but the cone, it doesn't really start with the cone, so where's this cone going to come from? So we know that the height is h and the radius is r, so the coordinates of that point will be r comma h. So where will we get this cone? So if we think about all the volume problems we did, where is it going to come from? Say rotating what? Rotating what?
Rotating that line about the y-axis.
Okay. Rotating this line about the axis. Or you can think about maybe even this triangular area, right? But that triangular area is really determined by this line, right? So if we're going to rotate that is like a door, triangular door around, that will give us the cone. So we really need this, right? Because all these volume problems we did, it gave us functions, it gave us equations that formed regions, and then so now here you have to come up with the formula yourself. Okay? So what is that? So you all should be able to do this, okay? You need to come up with the equation or the function for this line right here. So let's do it in red. I'll have it right. So what is it?
X. Do you take the slope?
Yeah, what's the slope?
R over H.
R over H. What do you guys think?
H over R. It's R minus 0 and H minus 0.
Okay, so the slope is?
R minus 0 over H minus 0.
Try again.
H over
H minus 0 to R minus 0.
H minus 0.
Okay, so H over R is the slope of that line. Y-intercept 0, so equation is? Okay, and so we're going to rotate that about the y-axis and just make it easier on yourself. I think pancakes, you could do shells, and that'd be delta x, or you could do pancakes. So probably, I'm guessing most of you tried pancakes. And so we need a good pancake is what we need. And then we need, let's do better here. Better? Okay. And we need a volume of a typical pancake, which is pi r squared h. And h is delta x or delta y? Delta y. And what is r? Okay, so what is the radius of the pancake? The radius of the pancake is the x coordinate. You should all be thinking that, right? You're all thinking that's the x coordinate. But we have delta y, so we got to get that x in terms of y. And that's according to this line, the red line, right? So x is ry over h. And so that's the volume of a typical pancake, right? Typical pancake at height y. And so we're going to add all those up from what to what? Yep, from 0, the smallest one down here at the origin, the biggest one up here at the top. And all this stuff is just constant, right? So really we just have the integral y squared. Which is y cubed over 3 from 0 to h. So we're going to have h cubed over 3. So pi r squared h over h is, or h cubed over h squared is just h, so you get pi squared h over 3. Volume of the cylinder. Cone. Thank you. Okay. Any questions? So certainly we've done lots of examples of volumes. We had washers, we had pancakes, we had shells. Definitely, of course, it's going to be on the exam, right? So given any situation, right? Not just particular examples that I give you. So for any situation, given any region, rotated about an x or y axis, rotated about a different line, can you come up with the integral for the washer or the shell or the pancake, and then can you set up the integral and get the volume? Any questions? And then you had some examples on the arc length, which I think the success was very high on the web work, so I'll just leave it at that. In addition to setting and doing those problems on the exam, you'll be responsible for that little derivation that I did of the arc length integral formula. Okay, it's pretty straightforward, and we took time to do it, so you'll be responsible for that as well. Okay. Questions before we do new stuff? Anybody? Yes, sir.
Do you mind getting the last question in the written assignment?
The last question?
Yeah, number 35.
Was that the
The-
corrugated?
Yeah,
Yeah, so was it setting up the integral or solving the integral?
solving.
Solving the integral. So was that the 1 plus cosine squared?
Yeah. But it said you use your calculators.
Yeah, so it said, it gave you the option, just use your calculator to do it. So it said that, right?
Yeah. It said you use your calculators to force it.
Okay. Yeah, I'm glad, because that was basically the form of square root of 1 plus x cosine squared x.
Yeah.
Yeah, so it told you could use your calculator to do it. And that's perfectly fine, because that's kind of in terms of doing it by hand, it's out of the range of what we did. Yeah. So, yeah, use your calculator. Okay, other questions? Okay, so now we're going to do 7.6. We're going to take a couple days to do this. Applications to physics and engineering. Okay, and here's the thing with this. The thing with this is that we're still applying the same principle we've been applying all summer so far for these 2 weeks. And so let's do it again. if we take the integral of a bit of change of Q, what does the integral of a bit of change of Q mean? If Q is just some quantity. Total change in Q. So in terms of these applications to physics and engineering, it's this all over again. And so on the exam, I'm just going to tell you right now, on the exam, it's going to be problems that are applications that you've never seen before because they're all the same. It's all about setting up an integral of getting a typical, whatever, typical volume, little piece of volume, typical little bit of change of a quantity, and then when you solve that integral, you get the total change in the quantity. So we're seeing this pattern over and over again. So on the exam, it's going to be, so we're going to do some work examples. So that's fair game for the exam, but on the exam, it may be a different type of quantity, all right? But it's the same. Can you apply this idea that it's the integral of a little bit of whatever you're trying to get the total amount of, right? Okay, so when we approach this section and we do examples, you really got to think of it like, I have all the tools to do it. I don't need to see Mark do 4 examples and then I'm going to repeat the example. So we want to come to each new example like you guys are going to get it without me showing you how to do it, because that's what the test is going to be like. Does it make sense? Okay. So we just need some basic formulas first. Okay. Work. Who remembers what work equals?
Force times distance.
Force times distance. But what if the force changes as you go? So what if force, say, is a function of x? So as you start doing work, the force is continually changing. How are we going to handle it? How are we going to get the total work? How are we going to get the total amount of work? What's that? Integral of what? So what are we going to do?
Many bits of work are added together.
Right, so we're going to look at a typical bit of work, right? And then we're going to add up those bits of work because they're all going to be different, right? They're all going to, because the force is changing continually. So we're going to get, this is the, so dW, which is this right here. That is a little bit of work. And when we do that, we'll get the total work needed to do whatever we're trying to, whatever task we're accomplishing here. Okay, so now some force formulas. So force is Kx, and this is for a spring. Okay, so in this force formula, this is the force needed to hold a spring at a displacement of x. So there's a natural length of a spring. So if you from its natural length, if you extend it x more distance units, there will be a force required to hold it there, right? Because it wants to pull back. Okay, so that's what x is. X is the amount of displacement from its natural length. Okay, and then this is that, and this is the force to hold the spring displaced amount x. To hold the spring displaced x units. Okay, K is the spring constant. That's just a constant value that's reflecting how stiff the spring is, how difficult it is to to extend it. So K is spring constant. So, for instance, the units might be newtons per meter, kilonewtons per meter, pounds per inch, etc. These are possible spring constants. Why? Because the more you extend the spring, the more force it's going to take, right? The more force it's going to take to hold it in its extended. So you have a constant that determines, like a slinky, you know what a slinky is? Has a super low, like a virtually zero spring constant, right? It's so easy. But like a strut on a car, it's going to have a very, very high, like the thing that goes on your tire for your shocks. That's going to have a very, very high spring constant. To move that thing, a couple inches, it's going to take a lot of force. Okay, so that's what the spring constant means. Okay, so that's for springs. Okay, and then the other common force formula that we'll need is weight force, right? So weight is itself a force. It's the force of gravity pulling on the object. So that is m times g. Okay? G is the acceleration of gravity. Okay? And that's either 9.8 meters per second squared or 32.2 feet per second squared, depending on what system of units your problem is. We'll see both. We'll see English and we'll see metric. Okay, so, and then this is the mass. Of the object. And then this is the weight. This is the force of gravity. So it'll be in newtons or pounds. Or kilonewtons or tons or whatever, okay? So the thing with Newton, let's see, metric versus English with this weight stuff. So with English units, we don't really use this because we go right to pounds. Right? We know that how much something weighs, then that's the weight force in pounds. In using metric units, oftentimes you'll be given the mass of something, and then using this m times g, that gives you the weight of it in newtons. So newtons and pounds is apples to apples, right? And so if you just have the weight, you don't need to do mg if you want the force of gravity on something, that's pounds or newtons. And newtons would come from if you had the mass and then times the mass in kilograms times 9.8. Okay? So kilograms and pounds are apples and oranges. Kilograms is mass. To get the force of gravity, you have to multiply the mass times 9.8. Pounds is force already. It's weight already. So if you have pounds and you want force, that's it. Does it make sense? Remember this from physics? Does that agree with what you've learned before in physics? Okay, so we've got a couple examples of force equations, and we know we got our work equation. And so again, if we want total amount of work, then it's going to be, we're going to find a little bit of work, and then we're going to take the integral over whatever distance we're doing that work. Okay? So let's try something here and see how it goes. So I'm just going to see how, we'll just give you an example and see how you do. So it would be easier just to, no, just type. I'll type. Okay, got all that? Can I erase? Okay. No, sorry. Okay, see how you do. See if you can pretend this is a test question, okay? You've got all the tools. You know how integral works, and you know the basics of a spring. So can you put that together and solve it like this is a test question? See if you can do it. If you try it by yourself, and then maybe in a couple minutes, if you're stuck, then start collaborating, okay? And I'm going to hand back some papers.
Oh wait, it'd be 0. Calc might could be 0. That makes sense. Actually, yeah, yeah.
Oh, and then you take 45 by that. 800. Or you get it from, and you say you take 3 more to get it from 5.
So you have to add
We don't have to say how much work is 15 to 18. So that would be your answer.
Okay, now I got 1, 5, 6. And you have to multiply that by. So from 1 to 5 That's the 800 constant. Right? And you pull 800 out, you just have X squared. Then what were you saying about multiplying by this? No, that shouldn't have to be because that's distance. Seems like because 156 like seemed right. Like it's but I see what you're saying. Where Newton's is their meter unit. Wait, of course. Wait, no, remember? Does it? It's been a while since I've actually. So does that?
It sounds right now. It's really powerful, but I don't
Yeah. Yeah, I guess that makes sense. I guess if you look at the Newton centimeters, you can keep the limits of integration in the centimeter. So I think that does work.
Okay, so we're gonna get. If we want the total work, it's gonna be the sum of all the little bits of work. So how are we gonna calculate a little bit of work that we do in stretching the spring?
Trying to find constant first.
Well, we got constant. Yeah,
Oh,
I got that. So you get the constant. You got this force and corresponding displacement of 5. That gives you our spring constant of 8 newtons per centimeter. So we've got the spring constant. Now we want to get a little bit of work, and we're going to sum up all the little bits of work to get the total amount of work. So anyone think they got it?
Force times distance.
Force times distance, right? Okay. What kind of distance? So as soon as you stretch it a further distance, what happens to the force? Increases. So if we want to get an amount of work, then what about that distance that we do it? Yeah.
Taking a origin?
We would get the force from 10 to 15 then from 15 to 18 and add them together.
No, because as soon as you start stretching it, the force is continually changing.
Yeah.
So how can we get a certain amount of force?
Integration?
Yeah. Adams.
Keep doing it for a bunch of small.
So for a very small amount of change, we can calculate an amount of work. As soon as we have a large change, then the force is continually changing. So how do you calculate that? So you're going to think about, we just want a small change in the length of the spring, which is, we'll call that delta, so called x, right? So x, so to get a little, this should be delta w, right? Delta w, sorry. So get a little bit of work is going to, we can only get that by if we do a little bit of change of distance, because as soon as we change the distance a lot, the force has changed. But if we have a small change in distance, the force is virtually the same at that place, right? But if you have a big change in distance, that force is no longer constant, right? So this allows us to calculate a small bit of work. If we keep that change small enough, we can assume that the force is constant through that little change of distance. Okay, so what is the force of the spring? That's not all of it. That's the spring constant. Force of the spring is?
Times distance.
Okay, times
Okay. X.
x, right? Times delta x. So we're thinking that because delta x is small, we've got a constant force over that small change. So this is, and we know that k was, we got 8, right? So we got it. We got our little bit of, or a typical amount of work, or a little bit of work. Same thing, right? Therefore, the total amount of work we'll do is summing up all those typical amounts of work. So force is 8x, little change in distance dx. And now what will x go from? From what to what?
15 to 18. 5 to 8.
Okay, I heard 15 to 18 and I heard 5 to 8. Remember what x is? X is the displaced length of the spring. So if we're going from 15 to 18, the displaced length is going from 5 to 8. Because x is the displaced length. So this is like the natural length here. So now this starts x. Starting from 10 is where x starts. So we're starting at having stretched at 5 to having stretched at 8. So from 5 to 8. So we got to watch our units here. So I just did the whole thing in centimeters. Okay, I kept everything in centimeters. This was what? This is newtons and this is centimeters. That's not division. So I'm working in newtons and centimeters, that's fair, and then I've got my x still in centimeters here, so everything agrees. So you got to watch units sometimes. You got to make unit changes where you need to. Okay, so this easy integral. 4x squared, 5 to 8. Did anybody get this before I did it? One person? Anybody close? Okay, so 4 times 64 minus 4 times 25, which I think is 156. So what are the units? Work is, the units are, so this would be newtons times centimeters, newton centimeters. But really, newton meters is more standard. So it's 156 newton centimeters. How many newton meters is that? Centimeter is 0.56 newton meters, which is the same thing as. So work has its own unit. So it would be newton meters, but it has its own unit. A newton meter is a joule. So it's joules.
How did you get the interval of truth?
What's that? So it said we're stretching the spring from 15 to 18 centimeters long. So the whole spring is going to be 15 centimeters, and the whole spring is going to be 18 centimeters. But this x is like I said before, is the displaced length. So it's starting from a displaced length of 5 and then stretching to a displaced length of 8, because 10 is the natural length. So that's what that x represents. It represents how much you're stretching it from its at-rest position. So if the spring starts at 15, then it's been already been stretched 5, and we're going to stretch it to stretching at 8 if it's 18 in the end. Does it help? Did you ask that? Yeah. So this picture kind of shows it. So this is the natural length, and then that's when x starts. Okay, questions on that example? Okay. Try something else, or more questions about this? All right. Okay, see how you do. So again, can you put all the tools together to solve the problem without me doing the example? This is where we have a high goal here. If you could do it, put the tools together instead of just following an example that I've done before. So I'll just give you a picture. there's like a pulley or something. So this is 30 meters. Long chain. And the chain's total mass is 20 kilograms. So let me just give you some little bit of tip here. Let's take X to be this. Let your variable X be distance down from the top of the building. That's a hint. See what you can do.
You're having
What is that? 19.6? Is that right?
Okay, so yes, if you fix the data side, that's why you should not. Okay, we're talking about one of the different directions, that's why you should. The reference point was. It's this is all one subject, the engineering, one subject. I think I
What is that? Did you do that?
Is 6.53.
6.53? What is that? Like the per...
Oh, we didn't multiply the distance. What? Oh, as it's getting lighter. Yeah, we missed it. Okay.
Okay, so if there is, what, X meters, I guess, yeah, you don't need to do that, but so if there's X meters, so say we already done a bunch, and there's X meters left, right? So this is a typical, we want a typical amount of work for some amount hanging off the edge, right? And that changes because as we pull up more, then what about the amount of force that's required? What's happening to the force?
Yes.
It's decreasing, right? So the amount of force is decreasing. The more chain we get onto the roof, the force is decreasing. So we just got this typical amount of chain hanging there, and we want to see how much work it takes just to pull it up a little bit, assuming that the force is constant for that little bit of movement, right? So, forces, or work, or delta W, is going to be force, delta x, right? Why? Because the force required is going to change as x changes. So we can only consider a little bit of change and assume a constant force for that little bit of change, just like the spring. Okay, so what is the force when x meters are hanging down? How much force is that? Well, if you do this, if you find the per meter weight, then you can just take the 6.53 times x. Now, you might have arrived at that a different way, and that's okay. But if this weighs 6.53 newtons for every meter, and we've got x meters, then that's the total force for x meters hanging is 6.53. And then we're going to times that times delta x. And that's going to be our little change in work. Okay, and then to get to total work, we're going to take integral from 0 to 30 of that. Do all our units agree? What is this? 6.53x is what? What's the units on that? Newtons. And what's our units on dx? Meters. So that agrees. So that's our little bit of work. When it's stretched x, or when there's x hanging down, that's the little bit of work required to move it up a little bit. And then we're going to do that all the way from x being 0 to 30. Questions? So that's super easy integral. And then the result will be newton meters. Anyone get that before I did it? One. Anyone close? Some people close. Some people close. Good. Okay. So how many did you get an answer? 29.5. 2,000 newton meters. So that's joules. Newton meters and joules, both. That's energy or work. Okay, now there's a different way to think about this, setting up the integral. So I just want to give you this alternate way to think about it. Instead of thinking about how much work when x is hanging over, we can just look at, here's a different way to think of it. You can just look at this whole chain, okay, and just take a bit of it, like this. Or just take the bit of it at a distance of x. All right, so think of that as the delta x. How much does that little part of the chain weigh? Right there. How much does that little part of the chain weigh? What's the weight or the force for that little part of the chain? So like, it's kind of like a delta F. So a little bit of the chain weighs what? 6.53 Newton per meter, or Newton per meter times how many meters it is, delta X, right? So that's like the weight of a little teeny piece of the chain. Now, how far do I have to move that to get it to the top of the roof? How far do I have to move that little bit of chain to get it to the top of the roof? X. So I'm going to take that little bit of weight, 6.53 delta X, so force, and I'm going to move it X times X. It's an alternate way of thinking about this. You can think about each little piece of the chain, and we just think of each one. We've got, so if it's here, it's a distance of X. I got to move that little piece of the chain up to the top, and then I got to move this little piece of the chain up to the top, and that little piece of the chain up to the top. Each one of those little pieces weighs this much, and it's got to go that far. And so then I'm adding all the pieces from 0 to 30, and you see the exact same integral. You get the same integral. Does that make sense? There's two ways to think about it. You can think about all this hanging down, moving it a little bit. That's the first way we did it. Or you can think about each little bit having to go a distance of x. And that's this way. So each little bit weighs that much. The work required, then it goes a distance of x. And you get the same integral both ways.
If we would have done it just without dividing by 30 to begin with, would we have just had to do that at the very end? If we used 196x?
But then does your integral make sense? Like, what was your integral?
Well, I use that because just if we didn't get the force per meter, if we just did the total force of the chain.
But so when you set up the integral without having divided by 30, did that have meaning? Was that relevant? Does it mean? I mean, yeah, in the end, that 30 is just a constant that is, but this has to make sense, right? Your little bit of work has to make sense. And I don't think it does without the case divided by 30. Okay, so now the chain has a bucket on the end of it. And we're hauling sand up. Okay? And the sand is overflowing. We're losing sand as we go. Fun stuff. Okay, ready? So here we go. Okay. So the chain of the bucket of sand is spilling at a constant rate, such that at first the total mass of the bucket is 15 kilograms. So when it's hanging 30 meters, total mass of the sand in the bucket is 15. And then when it reaches the root, the total mass of the bucket of sand is at 5 kilograms. Now how much work is required to pull the entire chain up to the root? think about right before the top. There's virtually no chain, but you still have the 5 kilograms at the top. Yeah, so, sorry, is that right? Okay, so yeah, so when it's hanging 30, it's at 35. When it's at the top, it's just the bucket of remaining sand, just before it gets to the top, and basically nothing of the chain, okay? So the question is, at x, what's your mass at x when x is hanging down? So how are we going to come up with that? How do we get that?
35 times 95.
You basically have a linear function, right? You have to come up with a linear function for given x, given any distance x, what is the corresponding mass? Did this turn out to be really easy? But anyway, so you basically have 2 points, right? You have the point 30, 35, and 0, 5. And you want, when it's x, what is the corresponding mass along that linear relationship? Anybody got it? I think it's just 1x plus 5. It turns out to be 1x plus 5. Because the slope is... Are you tracking with me? Does it make sense? We need to come up with a linear relationship for, given a distance x, what's the mass that's hanging there? And so it's basically you got ordered pairs, and you're going to come up with a linear function. Yeah.
Should this be 15 kilogram, not 35?
No, because you have all the total mass is the chain plus the bucket and the sand, right? At the bottom, and then at the top it's just right at the top it's just that 5 kilograms is left. Yeah. Okay, so you have to go with the linear relationship, and what's this mass given x? Right, so it's kind of like slope and y-intercept kind of thing, right? Slope is 35 minus 5 over, which is 1 kilogram per meter, right? And then the y-intercept is 5, so it's going to be basically your mass is going to equal. So this is slope, not mass. Unfortunately, they're both little m, right? So this calls the rate. And then the slope, or the mass, is going to be 1x plus, what x is when, what's the mass when x is 0? That's like the y-intercept, right? This is like your y-intercept. So this is going to be x plus 5. So we got to think about, we have a mass of x plus 5, and we need the work to move that up a little bit, considering that mass to be constant for just a little change in distance there, delta x. So what's the weight? What's the weight at a distance of x? Or the force, weight force? It's going to be mg, and the mass is x plus 5. G is 9.8. Okay, so that's the force, say, to hold it. That's all the force of what's hanging over the building. And then we want a little bit of work. The little bit of work to move that up a little bit will be force times distance. Force times distance. And then we want to do that as x goes from, we're going to add up all those little bits of work. as x goes from? So when x is 0, all the way up to when x is 30, adding up all those bits of work. Anybody get this before I did it? Do you agree with it? Does it make sense? So this is the key. You need this mass function, right? The mass is dependent on how far you are from the top of the building. And so since this is spilling out at a constant rate, you can come up with a linear function, right? Given the distance that the chain is hanging, what's the current weight? So you need this, or current mass, the mass given a distance of x. I kind of simplified out really nice. I didn't intend for the numbers to be that easy, but okay. So then you have the total force for it to hang at x meters would be x plus 5 times 9.8, m times g. And then you're going to add up all the little bits of work, which is your m times g times a little change in x, right? Or force times distance. Okay, any questions? Does it make sense? You also could have done it separately. Like you could have taken what you had before and just set up a new integral for just the bucket, and then added them together. That would have worked too. If you did that. You just consider the bucket. But you still need that. You still need this kind of linear relationship of what the mass of the bucket and the sand is. I mean, like, to be different than that.